Yeah, okay, so welcome back, everyone. So today it's my pleasure to welcome Lior Horesh and Sanjeeb Dash. And so they will be giving a three, actually, together with Christina and
Ryan.
uh, Ryan, who will be talking about AI Descartes and AI Hilbert. And yeah, so you're welcome to start, Lior. Thank you.
Thank you very much for the invitation. We are truly delighted to present some of our work to all of you. Before I start, I will provide you some of maybe the circumstances that led me to this research. Oftentimes, that's the only thing that people remember at the end of the talk. So I hope that it will at least give you one thing to recall. And at least for me, I started this work about a decade ago, somewhere with coincidentally with my midlife crisis, realizing that with my own gray matter, I may not be able to accomplish Nobel Prize worthy research, and especially as I notice more gray hair than gray matter, right? You start questioning whether it will ever happen. And at some point, rather than falling into the despair, I decided that maybe I should not give up, right? And if I cannot do that with my own gray matter, maybe I can build a machine that can do that for me, right? And that's really the story of this quest. Now, in the first slide, I will try to summarize the mission that not only me, also Sanjeeb and others have put forward. And thereafter, we'll provide you a little bit more of background as for the foundations of how discovery is done these days, and how it can be done, hopefully with some help of AI. So let's start with assuming that we have some observations of either a physical or not necessarily even a physical process or a phenomenon. We may also have some background knowledge that can be articulated in the form of theories and axioms and things of that nature. What we would like to do is to take both of these, put them in this Nobel Prize machine, and crack the handle once or twice, and hopefully get some nice symbolic expression that describe the relation between the input and the output that we have observed. But also, right, so this is one thing that we can pursue, but we would ideally also want to have a proof, right? Something that tells us, okay, you start with these axioms, and then you make these steps of derivation, and here you go, QED equals MC squared. That's it. And if all of that will work properly, the inevitable consequence would be getting a Nobel Prize. And at least the way that I was imagining this whole story to unwind was something like that. It used to be funny. I would say that lead in that I gave you until this year. And I'm sure that you all heard the DeepMind folks, they got the Nobel Prize for chemistry. So what Sanjeev and I would like to do is actually for the next year to have something like that, right? So that's our current goal. And let's step into the story itself. So when we think about the scientific method, we may ask ourselves first of all, okay, what is science at all? And science, at least in my mind, is the quest for understanding the natural world through both observations and reasoning. And the scientific method was inspired by René Descartes, that emphasized that there is a role for deductive logic and not only to empirical evidence in defining what the scientific method is. So this is one way that we somewhat need to balance the way that things are happening these days. And what we can, the reason we appreciate the scientific method, we already know that it has been transformative for socioeconomic growth, and it provides us a very principled way to come up with substantiated discoveries. And as I'm sure you all know the process, we start with a question, we then perform a study, we collect knowledge and data related to the problem, we form hypotheses based on that, we test the hypotheses, we make some assessment, we report, and the process repeats. Now, in the past few years, there has been a lot of concern and several studies that suggested that as we move forward in time, the rate in which new discoveries emerge is actually stagnating. It is slowing down. And that may lead to socio-economical or definitely economical stagnation. And if you look into this graph here, you can see on the green line describe the investment in some measures of how many scientists just roll, I don't know, at a problem or whatever, from 1930 until the 2000. And remarkably, the return on investment, this is the blue line, is on very well-defined decline, right? So this is somewhat alarming and concerning. Dirac was stating it is now more challenging for first-rate physicists to make second-rate discoveries than it was previously for second-rate physicists to make first-rate discoveries. And we would like to figure out whether that's it. The scientific method is just slowing down. We write all the low-hanging fruit of science, and now things are beyond our reach, or whether we can fight back somehow. Now, if we think about the fight back process, what is in our favor? So one thing to acknowledge at least is that many of today's challenges are things that cannot be necessarily solved by a single scientist. I will make maybe another comment on that. Recently, Trenestau gave a nice talk at the National Academies in the US, and he stated that many of the proofs that he's now tackling, and we are talking about apparently one of the smartest, if not the smartest mathematicians alive, that the problem that he tackles are too big, maybe for one person, so now they just break the problem into pieces. So we'll talk about it, but this is definitely something that we notice. We see big initiatives like CERN, where you have hundreds or even thousands of researchers working together towards one big goal. This notion of collective intelligence recently became more and more popular. Gone are the days where Atlas was the only, by himself, lifting the entire universe. Books like Sapiens advocate for the fact that we humans, our superpower is not strong clothes or big teeth or anything like that, but really the ability to collaborate flexibly at scale. And when we do that, we can really go very far. Now, when we talk about collaboration at scale, we can extend that. Why do we talk about only humans? Of course, we can collaborate also with machines. And even machines can collaborate with other machines, right? So we can take it not one step, but even two steps forward. Also in our favor, in the last few decades, we have seen more than 6 orders of magnitude in raw computational power increase. So this is definitely something we can utilize. And we see on the algorithmic side, unprecedented emergence of new AI capabilities. So all of that gives us some hope that maybe we can still scale the scientific method. Now, one thing that we may ask ourselves is, if we look into, there are various taxonomies that describe the different cognitive functions. You can ask yourself, yeah, all of them looks important, but what really lies at the top of that pyramid? And for years, there has been a debate whether this is a discovery or creativity that is harder to accomplish. And now with GPT being very creative somewhat in writing literature and making beautiful images and composing music and so forth, I believe that discovery is still a higher bar, because it's not only coming up with some creative proposition, but rather bearing the burden of proving that proposition actually holds in reality, right? So And the other question maybe for us, I'm sure that you've asked yourself that question before, where should I be if AI is coming to take many of our skills, right? So when the AI flood comes, what are the higher grounds that we should run to? And my proposition here, I guess, is to try to look into something like discovery as a task that is not yet being conquered by large language models. Okay, so now we would like to shift and talk about different discovery paradigms. And before we even describe the main two, we need to define what is the role of mathematical modeling. What we regard as a mathematical model is some consistent link between input and output of a system or a phenomena that we investigate. When we come to the craft of proposing such models, we typically make some compromise between the model complexity and how realistic the model is. But there are other types of trade-offs that we can consider, right? So maybe we would like to ask, what is the functional complexity of the model, how generalized it is, how robust it is, how interpretable a model is, and so forth. Now, there are traditionally a division to two paradigms of scientific or mathematical modeling. One is first principle models, where effectively we try to derive everything deductively from first principles. And the other approach is a data-driven approach, which is more phenomenological or empirical. When we look into the first camp, we see many famous names that came up with incredible realizations or discoveries about our universe. The beauty of the discoveries they made is that they are quite universal. And one of the examples I like to give is if you look into Maxwell equations, these are 4 very compact equations, and they tell you everything you ever wanted to know about electromagnetism. And not only that they do that, they also somewhat, I would say, oblivious or invariant to Lorentz transformation. So if your inertial system, you are in an inertic system that is moving close to the speed of light, those laws would still hold, which is really beautiful. Like how universal and elegant a thing can possibly be. The challenge is that it obviously takes a lot of time to come up with such new understanding of the universe. You can see the difference in the dates here. And also, it surely requires a lot of talent. So if me with my ego-seeking ambition to get a Nobel Prize wanted to have my picture here and maybe a few others along the side of Schrödinger and Euler and others, I admittedly, I don't have that talent, right? So this is one bar that is very challenging to overcome. Now, since we are in the business of Nobel Prize machine, we are not looking into just making one Nobel Prize award, but multiple of which, and our hero is, of course, Madame Curie, who was the first to receive not one, but 2 Nobel Prizes, both in physics and chemistry. So now to provide you a little bit of intuition into maybe some of the other side, right? So the other camp is the data-driven approach. And when we look into the mission statement of such approaches, it looks very similar to what we just described before. We attempt to find some link between input and output of a process or a phenomena, but when we read the small print, as a good lawyer should do, we find that it's typically done for a generic functional form. And the reason it is done for a generic or specific types of functional form is from very good reasons of computational efficiency, right? We are choosing those functional forms to be such that can be exploited and we can then solve big problems at scale. This approach is very sensible when we are dealing with large volumes of data. and when we have no or very little knowledge about the problem. So why not be data-driven if there's nothing else that can drive it? However, we do see that these approaches often fail to generalize, and since we choose the functional form prior to even seeing the data or reading about any background knowledge about the problem, we cannot expect to gain interpretational insight just from looking into that the equation or the form that the model proposes, right? So there's very little interpretational insight coming from those. Now, if we ask ourselves, okay, what limits conventional machine learning? One thing that we can see is the following. Imagine that the solid line is our truth, the behavior of some process or whatever, and the dashed line is our model. And now I'm going to bring some data in. So here is my staple. I will condition the model to the data, and okay, it looks a little bit better, at least at that point. Seems like a good idea, so let's repeat that process. Now I did that again. Somewhat better, but still not ideal. Let's repeat that, and so forth, right? So we can keep on doing that until we get a model that somewhat looks similar to the truth. So that looks great. Now, one thing that we may notice that we still have a tail, right? So on the right here, that doesn't seem to behave similarly to the true model. What can we do? So one thing that the data scientists may tell you, just bring more data. Okay, so let's bring more data, bring my better stapler this time, and now we're gonna really try to nail it. And unfortunately, despite bringing a lot of data, we may be able to represent this slot very, very well, but we didn't really do much to that other side. So in a sense, those models tend to be very good interpolators, but not such great extrapolators. And when we zoom out and ask ourselves, okay, so what should we do? Should we go with first principle or should we go with data-driven approaches? If you take your glasses off, you may ask yourself, you say, oh, it looks like neither of them is perfect, right? When one has an advantage, the other has a disadvantage, but there's obviously not a clear winner among the two camps. So that sort of implies that maybe if we ask ourselves, should we derive or otherwise let the data derive, maybe we should try to find a way to combine the strength of both rather than pick one camp rather than another. So that brings us into symbolic model discovery. One way to alleviate the limitations of many data-driven approaches is to state, okay, let's not have a fixed form proposition. Let's have a free form proposition. We would like to enable multiple functional forms, and maybe one of them will be closer to the one that described the underlying phenomena. Maybe I should have said in the previous slide that part of the problem here with the extrapolation is that no matter how much data you're going to bring, if the functional forms of the model and the truth are dissimilar, even if you can condition them to behave nicely at those observation points, the moment you stop doing that, they will diverge indefinitely, right? So that's the problem of functional form dissimilarity. And the way to maybe to try to overcome that is, okay, let's not have a fixed form. Let's propose a free form proposition and try to find both the functional form and the parameters at the same time. Now, this sounds like a very good but yet very naive proposition because there are infinitely many functional forms and models that will map a set of points to a set of points. So how can we overcome that challenge? So one resolution is to not only propose a free-form model, but also try to minimize model complexity while we ensure that the model is indeed predictive, that indeed the points are mapped to other points. And even more than that, maybe there are other virtues that we would like to honor, that we would like to impose upon that model. So, Sanjeeb, may I let you continue with this section now? Yes.
Yeah, sure. So, as Lior talked about, we are right now interested in symbolic free-form discovery, and one particular approach and algorithm towards this is called genetic programming. Is there some light? Do you see a light reflection on the screen? Okay, it doesn't matter. That's only on my video. So anyway, so and this was initially posed by Dexter Koza, and he has a very nice book on it, Genetic Programming and the Programming of Computers. This is a very broad area. There's a huge amount of research on this. And the point is to use genetic algorithms. The inputs are, just a second. So I'm going to share my screen. Give me a second, please. I'm just so sorry about that. So as this is opening up, I'm just going to. This is a big file. I'm sorry about that. It's taking a second to open up. So I will just take a second and then open it up. Jump ahead to the. I'm sorry about this. I had not anticipated this would take so long to load up here. All right. So we were out here, symbolic regression done by genetic programming, which is a particular type of genetic algorithms, rather an application of genetic algorithms. The idea is you start off with an input operator list. And the operator list could be a pretty general list like plus, minus, multiplication, division, log, sine, cosine, expression. Typically, depending on the context, you'll choose a subset. Then you have some data like X is a matrix. Each column represents a variable. The values of a variable and each row is a data point. Y is a vector, so the output for each data point. And the goal is to find a function y equal fx that fits the data. One common objective is to minimize the tree size plus accuracy, y tree size. So it's in this symbolic regression using genetic programming, a standard approach is to represent each formula using a parse tree. The same way it would be processed maybe inside a computer program like Lisp. And on the right, we have a representation of a parse tree. And the parse tree can be, by the way, general. It doesn't just have to be mathematical operators. They could be logical operators like if and greater than and stuff, things which are used in full-fledged computer programs. So the way a computer program can be represented by parse tree, you can do the same for a symbolic mathematical expression. And the goal is to learn these sort of parse trees which fit the data well based on genetic algorithms. And so the idea of this genetic programming approach is to create an initial population of random functions using operators and variables. And here are some initial examples. So for example, the way you read each formula, you start from the top, you take the formula of the left subtree and the right subtree and add them up, and then you repeat. So you start with an initial population, you calculate the quality of the fit, and now let's say we define the fit as how well the function defined with the parse tree does in the data, maybe the accuracy, error, etc. And then you also calculate the tree size. And then you can combine them. The reason for the tree size is that genetic programming often leads to very large trees. And then in a subsequent pass, you take the initial population, then you combine different formulas in different ways to get a new population of formulas. So two standard ideas are, one is of course reproduction, the same formula goes on to the next stage. But then what you can do is any subtree of a tree also represents a valid formula. So you can take two different subtrees from two different formulas and just swap them. And that's what people call recombination or crossover. So for example, the subtree on the left with the root as a division, and the subtree on the right here with the root as the multiplication, they're swapped. Then you get the two subtrees on the left with the different formulas. That's a new generation of formulas. You test for accuracy and then you do. So now what we have done in this war, what we did subsequently, and not just us, but there are a couple of other groups, is to look at a different approach. Instead of doing this purely heuristic search-based approach based on genetic programming, to use a mathematical optimization approach where you formally encode the tree you're looking for or the class of trees as a set of solutions of a collection of equations. So, and the way to do that is that let's say you think of a tree, we have variables representing what expressions go into each node of the tree, which original variables go in which leaf nodes of the tree. So you can think of them as auxiliary variables in your mathematical optimization problem. And then you try to solve for that. So you have constraints encoding the fact that you have a valid tree and so on. And it's a fairly long optimization problem, a lot of different constraints. I won't give the full details here, but suffice to say, we can define it and give it to a nonlinear optimization solver if the trees are not too large. And then in that case, we can do things like, say, minimizing the complexity. We can actually say we can find the least complex, and sometimes the problem is, not too many variables. We can even get a certified solution. We can say that we truly have an optimal formula given the list of operators and the tree size in terms of, let's say, the complexity. We have the least complex formula, which has a certain bounded level of accuracy. Or you can change the objectives and put something in the constraint or something in the objective. And this is done by a couple of different groups, as I said, including some people including a recent work by Kim Leifer and others in Informs Journal. So now, sorry. So going ahead, so we did some, we tried this code on a couple of different examples. So an early example was Galileo's formula for the pendulum. He noticed, many years ago, he noticed in the 1580s that the wind caused the chandelier in the room to swing, and then with his own pulse, he could measure the swing and figure out that it always took the same time, even though the size of the amount traversed, the distance traversed by each swing might decrease over time, but the time taken by the swing was more or less the same. And he invented a pendulum for measuring time. So what we did in, let's see. I'm just trying to run the demo. So what we do in this particular experiment is we actually created a mechanical, a device which has a bunch of pendulums different lengths, and we let them fluctuate, and simply have time recordings of when the pendulum is at a certain location, and then try to learn the formula for this relationship between pendulum and length. And how does with this symbolic free-form solver which we created, the formula is given right here on the top. It's square root L, the length, times j minus I pi over square root of g. And so I won't get into all the details, but the important point is that it's a very relatively compact formula, and it can be represented by a relatively small parse tree. And we were able to do this using our mathematical optimization techniques. If you use things like DNNs and neural networks, of course you have we know that they can approximate essentially any function, even with just a small number of limited set of primitives, namely multiplication, addition, and the functions which you use in the nodes. You can still get more or less approximate any function. So of course you can approximate this formula, Galileo's pendulum formula. However, you typically need a lot of data. In this particular case, we're able to work with a relatively small amount of data and get a function which generalizes very well, and and we can certify it. In this particular case, we're able to certify that this was the optimum pendulum if the data was not confusing. And we also then looked at a particular data set which was created from the Feynman's lecture series by in a paper called AI Feynman. Paper and the associated software system is called AI Feynman. So what they did is they took 100 formulas, created simulated data sets, and ran and used a code, and we were able to especially in the situation where there's a little bit of noise, we were able to improve over both AI Feynman and Eureka. Eureka is a genetic programming based method. AI Feynman is a method which combines genetic program, which is not genetic programming based, and we were able to in many situations improve over that. In particular, when we looked at all the 100 problems, out of the 100 problems, we cannot tackle a few. this particular method, mathematical optimization method, we could not use trigonometric functions because the solver, the nonlinear optimization solver we're dealing with, could not deal with trigonometric functions. So but if we leave aside some of those, then we were able to do pretty well compared with the state theory, especially in the presence of noise. Sorry, I jumped ahead. Now, one more thing to notice is what happens about constants. So, when you're doing a symbolic regression, neural networks, etc., you don't know, for example, that you might have a 2 over pi somewhere. And so, especially in situations where you have waves, you have fluctuations, periodic functions, pi occurs frequently. How do you deal with that? Now, in some cases, AI Feynman is sometimes able to deal with that because what they do is in their system, they explicitly throw in pi as a variable, let's say. So they're going to work with pi as a variable and use that in triangular different formulas. Now, we can do the same. We can, in our system, we can basically use admissible operators and some numeric constants, and then try to find combinations of these constants which can be used, which show up in the final form. In particular, what we can do is if we find a numerical constant in the formula and then we wonder, is this somehow some combination of known constants such as pi, e, etc., then we can throw them into our optimization formulation and then try to find some combination of these known constants which gives you this unknown constant. Like say 2 over pi, you'll get some value for that, and then now you want to see if that is equal to 2 over pi. So we throw in small integers, unknown constants, and then try to find small integers and known constants, and try to find unknown constants as a function of those known constants. So now, why does knowledge matter? And in these situations, we're working with data, but if the moment you start having noise, what AI Feynman is a particularly interesting experiment they do is if they have zero noise, even with 10, 15, 20 data points, they can often find the original function back. But the moment you add noise 10 to the 0.01%, 1%, it becomes much, especially to the level of 1-2%, which is pretty common in many physical situations. So you can imagine astrophysics errors probably higher. It becomes much harder to get the right function back just by doing regression type exercises. They're basically a very, very large number of functions which can fit the data closely. And so, so then it helps a lot if you have knowledge which can then guide you towards a sort of a reduced search space of functions. So instead of finding just functions which fit the data, you find functions which are consistent with some background knowledge and fit the data reasonably. So there are many examples in history where people have where people notice that there's some perturbation in the data. Some data is not the way they expect it to be, but then they use then they make some assumptions that if the data is noisy, it's maybe because there is some other planet around, and if there was some other planet around, then they took into account existing theory. For example, Le Verrier, he concluded there must exist some planet perturbing an unknown planet, perturbing planet, which was creating perturbations in the trajectory of a known planet, because he assumed that the theory, all of Kepler's laws, Newton's laws, etc., hold, and therefore the perturbation was being caused by something else. Now, of course, even when you have some background knowledge, one tricky situation could be, especially when you're in a new scenario, where maybe your background, and this happens a lot in chemistry. So, for example, chemistry, we know, let's say that some materials behave in a certain way in a certain range of temperatures, but they behave very differently outside that range of temperatures. So the knowledge itself might not be fully consistent with the data, might start becoming to be an approximation. It can be incorrect, it can be incomplete. And just the way data is often noisy and sparse, etc. But the whole point is it can still significantly improve your performance in terms of finding formulas that fit the data, and results. And that's a lot of what we did in the work, which we'll be talking about more in a lot of detail in the next two lectures. But I'll try to give some high-level ideas of what we do in this. So I'm just going to go ahead. So to the next slide. So one thing about one other thing about knowledge in the use of scientific discovery is that you can we had so let me give a concrete example of and Lior, do you want to take over from here maybe? Lior, could you take over from here?
Sanjeeb, do you want me to proceed?
Yes, please. Yes. Then I'll get back when we do the
okay.
the chat GPT.
I hope that I'm hopping in the right place. But one thing that we can appreciate is that the value of information, right? We often ascribe a lot of value to data. We may need to figure out how much value we attribute to knowledge. And this is and even taking that another step forward, we may ask ourselves, how do we compare the two, right? Well, what is the value of knowledge compared to data? How many data points are equivalent of one new axiom, for instance, right? This is just to illustrate that. And at the time, Democritus stated, I would rather discover one true cause than gain the kingdom of Persia. So just to demonstrate how important it is to have more knowledge or more truth discovered. Sanjeeb, can you skip to the next slide, please?
Yeah.
Or if you want, I can share on my side. So just to give you a briefer as for when we speak about formal methods and logic, what do we really mean? So I'm sure that you all have seen that before. I just will sort of recap. Axioms are basic assumptions that are given without the requirement for any proof. Literals are propositional variables or the negation of which, such as A or not B. Logical connectives are symbols that combine one or more propositions into more complex propositions. So for instance, we can talk about conjunctions, disjunctions, negation, implication, equivalence as some logical connectives. Next are the logical inference rules. So if we would like to take new clauses, we would like to derive new clauses from existing clauses, logical inference rules such as resolution, induction, refutation, reflexivity, and so forth enable us doing that. A theorem is a statement that has been proven to be true without using proven to be true using those axioms and other theorem that has already been established. And the proof is the way to get there, right? So we start with the axioms and we do logical inference until we get a theorem. All of that process was the proof. So next one, please. Now, if initially when we spoke about symbolic regression, we already opened a broader aperture to the machinery we can use when we do mathematical modeling, and that involved variables, involved constant, and involved arithmetic operators. We can actually make the broaden the scope even furthermore. So next click, please. By virtue of bringing in all these logical connectives, right? So we have those other tools that we mentioned. And one thing to distinguish is between two classes of reasoning. So there are actually more than two, but two that are more relevant to us. One is inductive, the other is deductive logic. When we talk about inductive, one click, please, or maybe it's better for me to share instead of you. It would be easier to do that.
Okay.
Can we switch for a second? So one mean to do that is to we start with observations. We try to identify patterns within those. We form a hypothesis, and then we try to see whether that hypothesis is consistent with the theory. And that's inductive logic, as opposed to the more maybe conventional means that we think about logic. We start with the theory, we start with the axioms, we make a hypothesis based on that, and then we make some observations, and we confirm that indeed the new theory that we devised is indeed correct, right? Or at least consistent with empirical evidence. Now, the next step is to look into how these things are actually being done in action. How do we perform logic? And here is a very high-level explanation of one approach, which is called differential dynamical logic. And this is done with what is called cylindrical algebraic decomposition, also known as Collins decomposition. The way that you may want to think about that is, imagine that I have functions, f1 to fn or whatever. These are functions from Rn to R. Each of them is representing a truth in or false, right, given the assignment. So I will provide an assignment x that may satisfy that fi of x is larger than 0 or not. So there is a claim here, a statement, and that statement will be a function of x. And now I would like to figure out whether I can find an assignment x where all my claims are satisfied. All these functions, all these inequalities are satisfied. And one thing that we will immediately observe is whenever, because we are talking about inequality, the interesting places to look for something that can change is at the boundaries, right? Wherever those fi of x equal to 0, something may happen beforehand or after that in terms of the sign of the fi functions. And we would like to then take Rn, divide it into different segments, and based on those equalities, and then try to find is there's an assignment of x where everything is holds, right? So true for all of those assignments. And you can actually do that. It's not very efficient to do that, but this is one way. You can see this nice image of the division of the different spaces, and that would be one way to geometrically think about logic. There are other methods that are based on SAT solvers and other solvers, but on a very high level, that, you know, these are some of the machinery that one can employ. Now, one interesting question we can ask ourselves is, everybody are now stating that generative AI is the right way forward. Should we really go through all this very complicated mathematics and logic, or just go to ChatGPT and ask, okay, here is a problem, here are the axioms, here's the data, tell us what you can do. So let me give you some examples that we have explored. Sanjeeb, do you want to do that, or do you want me to?
Yeah, I can talk about it, but I'll let you continue the sharing. So okay, the basic idea, the basic idea we tried out was to take some of the functions for which we use our systems and say, what if we give them to ChatGPT, in particular model GPT-4o, the most recent one from OpenAI. So we give an input question as text, and we get the output as text. And there's some very impressive things, but let's go through that. So first one is we pose the question, and the question we pose is exactly as typed out above. Consider the following points of the mathematical function f of 3 variables m1, m2, and d. And we give the function values for 3 possible data points. So values of m1, m2, d, we give the value of the function. What is the expression for the function f? So in this particular answer, I give only the partial answer. It proposes, it says given the points. So first interesting thing, it recognizes m1, m2, and d variables. It puts them in LaTeX or with subscripts, m subscript 1, m subscript 2, and so on. And it says, well, let's consider a multiplicative or power law model. And it gives the possible model type, and it actually gives some Python code, which I'm not showing here, to find the best values of A, B, C, and D for this model. Next slide, please. Right. So then we decide to do something more sophisticated, and we actually give it some background theory. We say consider these following points and their additional variables f, g, f, c, w, d1, and d2, such the following relationships hold. And these relationships come from from Newton's laws. The Fg, the equation 3 is Newton's gravitational law, and so on. Without the gravitational constant, we deliberately drop the gravitational constant in this case, and ask what is the expression for the function f. And if you look at the answer, it again puts formats all these input equations nicely. It recognizes their different variables and starts and does a almost seemingly magical solve. So the step one, and then if you go to the next slide, please, here. So it does a complete substitution variable, of all the variables, and gets this beautiful expression on the final expression for f, which is essentially Kepler's third law without the gravitational constant g, which we assume to be 1 in this case, which you can assume depending on how you measure depending on the units you use for mass and distance and time and so on. So, and it says that this expression satisfies the relationships provided. So we try for a different problem. So Lior, next slide, please. We decided to try it for the Einstein's time dilation law. And in Einstein's time, excuse me? Any questions? Okay, if not, so we pose the question that on the left you have the text which we give as input, and on the right this is the answer which comes out from ChatGPT. The interesting thing as we go on to the subsequent slides, you'll notice that in equation 8, it specifically recognizes that c is the speed of light, 3 times 10 to the 8. And next slide, please, Lior. And notice we did not give meters per second, but it recognized and put in meters per second. And then it again goes through some beautiful derivations, and it does a lot of interesting substitutions. Next slide, please. And it gives the correct expression, Einstein's time dilation law, as a function of relative velocity between two different clocks. And so then we ask the question, how did you find this derivation? We are curious to know whether it's using a theorem prover, what's happening. And if you look at the next slide, you start noticing that it even recognizes what the variables are. So the previous, okay, can we stay on the previous slide, Lior?
Sure.
Yeah. So it recognizes here the fact that c is the speed of light. It says it's common in wave propagation, dt0, dt, etc. It recognizes what these are. It recognizes L is the effective path length and so on. So, and we did not give any of this input. So you realize that there's a lot of statistical information which was present in this problem. There are probably these existing derivations. And what we were told by colleagues who worked on this, that if we were to change the names of the variables, and that's what we mentioned in the bottom left, we just rename all the variables as A1, A2, A3, A4, and the C is not present, the fact that it's the speed of light, and suddenly it collapses. Suddenly it cannot provide this derivation. It does not, its performance degrades drastically, and it cannot find the correct formula. It does a limited set of substitutions and it stops. And even worse, if you go to the next slide here, we specifically gave a function which we derived and which we created as some sort of artificial function which we know the formula to. And we give the question, and you can see the answer. And then on the right block, you can see in step 3, underlined in red, it doesn't even do the basic math correctly. So it says, oh, I found a function, and it proposes a function 2 to the power d times k times z times g. But when you look at step 2, inside step 3, sub-step 2, you see that it evaluates 2 to the 0 times 2 times 2 times 2 as 4. And then similarly, the next line, it evaluates 16 instead as 8. So you realize that that it's not even basic arithmetic is not being done correctly in this. So what we realize is that at this point, at least, it almost can seem magical if something similar has been done. But if you change this, so we deliberately created an artificial function in this particular example. So we created a function, just an arbitrary synthetic function, which was maybe not studied in the literature, and gave it a ChatGPT, and then it doesn't do as well anymore. And it doesn't even do the math correctly, basic arithmetic correctly. So there are still serious limitations even in the state-of-the-art generative AI tools. However, in terms of a search engine for a lot of existing science, it might prove to be very powerful. The very fact that it recognized the C was a speed of light, used it, that's a very impressive, I would say, it is very impressive. Lior?
Yep. So just to recap that, effectively we can indeed see that these systems, they may act as if they can reason, but in practice, what we observe over and over again is that they are doing effectively a very elegant means of approximate retrieval, right? So if something has been seen before, they will indeed highlight that, but they are not performing systematic reasoning. To do that, by the way, so even propositional logic is NP hard. So if they can do that, if a cheap polynomial algorithm, I'm saying cheap in a very positive terms, right? I mean that cheap effectively doesn't require a lot of resources, then that implies that P is equal NP. And as of now, it's not proven, but we suspect that that is not the case, right? So it will be very hard to do NP hard, to solve NP hard problems with something that is actually a polynomial, right? Now let's take another quick step forward to ask ourselves, okay, can we collaborate with that, right? So we saw what it can do. It wasn't enough, apparently, but we should not completely disregard the amazing capabilities. If we ask ourselves, what is a mathematician? Once you add here the cup of coffee, we all have this joke about it's a machine that consumes coffee and produces theorems, maybe some other artifacts as algorithms, analysis, and so forth. And we can definitely use some help, even in scoping what problems you should consider, how to abstract it, maybe have a good colleague that will complement our skills, help us to even learn something on the long run, provide some criticism to things we do, help to orchestrate a study, prioritize what we should look at first, scale study. So we hope that actually AI can help with all of that. I want to give you very quick a few examples because we are approaching the end of the hour. Too soon, but it comes. So one example is a study that DeepMind did, in which they look into knot theory. And in knot theory, you have different signatures for different knots. You have so-called algebraic signatures, and you also have geometric signatures. And the question is whether there's any link between the two. There was no known connection, let's say, between Jones polynomials and Chen-Simons. How can you figure out whether there is a link? They propose something almost obvious, right? Let's just put a neural network in between, try to see some examples, and then provide a new set of unseen knots. If we are capable of predicting one signature from another with a probability that is beyond random, then apparently there's something there. So that proposition is very effective in even figuring out what question to ask, which is may sound obvious, but if you are not asking the right questions, we can work very hard to address non-important problems. So this is one way AI can help us with. Another problem that we all face, I guess, is we often have a problem that is just too big for us to handle. And a chain of thoughts and other such propositions have very elegantly took big problems and broke it into smaller chunks that are more manageable. You can even do that with theorem provers. This is work that came from our group called the graph to tack, that effectively take a proof and breaks it into smaller pieces, and then each one of them is manageable. It's easier to solve, or can be solved with a different agent, and later on be assembled into bigger, more complex composition. Another quick example is if we look into the relationship or collaborative relationship of having Gen AI providing hypotheses, generating hypotheses as a substitute to symbolic regression that we discussed earlier. And on the other hand, have a formal verifier that will say, yes, it works or it doesn't work. So again, a DeepMind study took the notion that Strassen back in '69 found that you can do matrix multiplication 2 by 2. You can reduce the number of multiplications from 8 to 7. Vinograd, that was my former, I guess, head of the department, proved that you cannot go to 6, so 7 is apparently optimal. DeepMind, with a lot of computational power and persistence, found not for a general, but for specific structured type of matrices, 4 by 4 binary matrices. They found that you can reduce the number from 49 to 47. It's not a very big news, but it just showed that you can have this sort of proposition. Another study that came from their end is the alpha geometry. They beaten to death a system using RL with 100 million examples or so. And maybe it's not surprising that after you see 100 million examples, there's nothing that you didn't see before when you go to tackle something like the Math Olympiad. But still, they actually used a formal method as a verifier rather than just relying on populating problems in a somewhat generative fashion, right? So this is what I wanted to highlight. Another interesting example is the first computer-assisted verification problem came about for the graph coloring problem. Back in the time, they asked whether the counties in the UK, not the US, can be colored with a small number of colors and divide without repeating, without having a red and red on two neighboring. Maybe I should be careful with the colors now. Yellow and green on two neighboring states or countries. Kelly proposed that it can be done only with 4 colors. It took almost 100 years before Apple and Haken simply populated all possible scenarios somewhat logically through a computer and did formal verification, and that was the proof, the first computer-assisted proof. Our own work, and you will hear more about it next week, but I just want to give you like a very quick preview, has similar flavor, right? We have a generator. So here are some modeling primitives, grammar and data. Symbolic regression can be regarded as a generator. It produces a bunch of hypotheses. Those hypotheses can have a different order according to fidelity or complexity. You then bring your verifier. So here's the background theory. Here is a reasoning agent, a formal method, the automatic theorem prover, and do one of two things. If you have all the background theory necessary to derive the relations from scratch, you would actually provide a full proof of derivation. In reality, that's rarely the case. Typically, you have partial knowledge about the problem and partial noisy data, and then you would effectively ask a different question as for how far, maybe geometrically, one hypothesis versus another from some, let's consider that as a sub-manifold that represent the intersection of different body of background theory, right? So there is an implicit surface that describes a convergence of all the things that are satisfying the theory. It's an implicit because we don't have enough theory to reduce it to a point, to a single hypothesis. And yet we can ask how one hypothesis or another close to that surface and provide a measure, continuous measure of derivability. And with that, we can reshuffle, reorder the hypothesis list according to derivability and hopefully come with a substantiated discovery. Lastly, on that sequence, right, is the work that we did very recently with the AI Hilbert. So effectively, we ask ourselves, can we, rather than sequentially come up with a hypothesis just from the data and verify it with the theory, can we combine the two steps into one? And the answer is yes, you can do that with some nice algebraic geometric machinery that came from David Hilbert, and really change this arc from hypothesize and test into a single arc of hypothesize, right? So I know that we are at the end of the hour, so I'll skip that, and we'll get to the almost to the summary. So AI can be instrumental in service of the scientific method. It can help us in many, many aspects, as we saw, from asking better questions to collection and standardization of knowledge, composition of problems, proposing hypotheses that are more interesting, or even embracing hallucinations to come up with crazy suggestions as for what what could be an alternative theory, and so forth, experimental design and so forth. It can be truly instrumental. Now, just to recap and summarize, we started with a big question: can we scale the scientific method? And in our view, yes, we can do that, but we have to disrupt this whole process. We cannot just take yesterday's algorithm on tomorrow's computers. I don't want to. So DeepMind are doing a great job, I guess, at that. This is not the only way, and I believe that's not the right way even to do that. We really have to think about different paradigms to do that. Ideally, we would like to come up with discoveries that foster discoveries that are universal, derivable, can even learn from small and noisy data, and equally with imperfect knowledge, and hopefully even simultaneously unify the two, right? Rather than have a pipeline. So here is just the ladder that we try to climb here. And now, if we do all of that, we hope that such systems can help us to make discoveries that are beyond what either a machine or a human can do. And next on the series, we'll have Christina Cornelio that will describe to you her work on AI Descartes. And the week, I believe after that, Ryan Corey-Wright will also describe the other system that I mentioned, the AI Hilbert. Yeah, so with that, we really want to thank you for your attention and for listening. We hope that you find it exciting. We are very open to collaboration. So if this is something of an interest, please reach out to us and let us know. Thank you.
Thank you very much. Thank you. Thanks. Just a correction. So the talk are in 2 and 3 weeks, not next week. Okay. Because there was someone else who was scheduled for another talk. Yeah. Anyway, any questions from everyone? Yeah. Yeah. Please, Louis. Yeah.
Yeah. Can you hear me?
Yeah, we can. Yeah.
Okay. That was a nice talk. I'm reminded of a talk and some things I read by someone named Hod Lipson, who is now at Columbia, who did something that I didn't see done here, and that was to take data and derive a differential equation that generates the data. In one case, he derived Lorentz famous equation, the butterfly effect, and the actual trajectory led him to the correct equation using a kind of genetic approach. I don't know enough about that to understand it all, but he ended up with the right equation. And along the way, found that you had to be careful how you did it, that you did come up with trivial things. But I'm wondering if you have done that. And I think that's important because a lot of laws of physics and other areas in science are expressed in differential equations or more equations in a way that will generate trajectories and so on. Rather than coming up with a formula, you're coming up with the equation that generates it. I'm wondering if you've done that or have anything to say about that.
So I love your question, Luis. I cannot agree with you more because I come myself from the differential equations background, and I have nothing but appreciation to dynamical systems. We looked into dynamical systems derivations. Some of the results you will see in the talk of Ryan with the AI Hilbert. We believe that there's a lot more that should be done and can be done. We are looking into that with differential algebra and differential geometry. So we are trying to bring some of that machinery into the picture. We are very closely familiar with Hod Lipson was I was an adjunct professor at Columbia, so he was in a neighboring department. Some of his work was motivating many others to look into symbolic representations. I do think that one thing that was lacking there and we can now look into is purely data-driven approaches has some merit, but they have a limitation, especially when we look into problems that has a physical instantiation, right? So we look into differential equations. We can talk about conservation of mass, conservation of energy. We can talk about closure and boundary conditions. All of those things can be articulated relatively elegantly in symbolic form with as theoretical background knowledge, and the moment we bring all of that together, I believe that we can do even more, right? It's not just here is a proposition that seems to match all the data points that you've seen, but we can go beyond that. We can also provide the assurance that whatever differential equation has been derived, it is also consistent with everything we know about this class of problems.
Thank you.
Well, thank you.
Other questions?
Lior, I spoke to you about this in Toronto a little while ago. I wonder if you had time to think about it. But when you're composing these graphs from several little operations that pluses and minuses and divisions and such, is there any scope for having some of the operations be themselves learned objects? So maybe like traditional neural networks.
Yeah, that's a great question. So in a sense, the fact that we choose, let's call those arithmetic standard operators is merely a matter of our own convenience. I agree with you completely, right? In some regards, you can learn new operators. Maybe it will be much more appropriate than prescribing a set of operators that will limit the scope of hypotheses that you can provide. The challenge in doing that is potential interpretability, right? So you may come up with some new operation that may not have a lot of interpretational insight, or will be harder for us to interpret that. But yeah. I'll be curious to look into something like that and ask. Maybe we can do more if we bring learned operators. We can abstract better, right? Like we know that this notion of abstraction is to at some point say, okay, maybe this and that. They are really trying to tell us that this is a sine function. Why do we represent that in such a broken, crooked way, right? Like you can represent with Euler equation a sine with two exponents. Maybe just have a sine, and it is more efficient, right? So maybe we can learn other more abstract operators in such a fashion. So I like your proposition, Tom. I think it's a good thing.
Yeah, I'm seeing the problem is, I mean, maybe if you're already willing to give up interpretability, but I think the more immediate problem is just actually optimizing this, because now you have kind of two competing optimization objectives, both the outer problem of the mixed integer nonlinear program that you're doing, and then some inner problem of actually finding those modules, which those have to be trained somehow as well. So I'm not really sure how to mix those two optimization problems together. I just wondered if you had given any thought to that sense.
Right. So I don't know, maybe Sanjeeb is more knowledgeable about mixed integer nonlinear programming than me. Do you have a better answer than what I will propose?
Why don't you go ahead first, and then I'll.
We can talk also offline later.
Yeah. So Tom, my intuition is our own specific choice of mixed integer nonlinear programming is one viable proposition among many others to generate hypotheses. We should not be married to that. The reason we favored that at the time was with such machinery, you can provide under some conditions a certificate that the expression that you found is indeed globally optimal, right? So in other words, that one cannot find a better means simpler or lower error expression
Do you hear me?
Yes.
Okay, sorry, I have some technical problems and maybe background noise here, but given or granted that you covered mathematics and physics, maybe we can go to chemistry and biology, and specifically, would you be ready to look at predicting catalyst? Who is catalyst? Who is new material that will be viable in medicine? And also sort pathways in biology and medicine. Some of those pathways, flowcharts, one can get lost there. And the question is, do you have now a flashlight to find my way in the non-random forest, which is life?
A wonderful question. We haven't looked into biology so far. I believe that we should. The main reason we didn't do that is our ignorance, right? We have very little knowledge about the processes and catalysts and interactions, which are very complex in the biology world. But I'm very open, right, for collaboration. So I'm happy to bring our own flashlights if somebody will open the door and to us, and together we can try to find something in the dark, right? I hope that this can be done.
I'm just familiar with Amos Corman, who is looking at wild ants with very unpredictable behavior, but he manages to find some prediction there, maybe with AI or with other gymnastics. And I'll be more modest, asking to understand cell-cell interaction, cell decision, cell fate, and wild or not wild protein behaviors.
So I we'd be very happy to collaborate. I admit my knowledge of cell-cell interaction is limited, right? I know that they can signal each other. They can do some other means of communication, but yeah, if we can distill a specific problem into the data we have and some knowledge, and I think that you may actually touch on another point that is important here, because previously we could only handle very rigid knowledge, and that was some of the precursors to the cold AI winter that we faced many years ago. We would like, and we had made some steps, and I hope that others as well, towards bringing more forgiving means to do logic. And the moment you are capable of incorporating inconsistent background theory and knowledge, but still somewhat viable information, together with the data, maybe we can discover something that we couldn't discover before. So I know that in biology, that's one other reason that we didn't go there yet is it's a little bit more challenging to talk about, I believe, conservation laws and things of that nature. The processes are a little bit more complicated, even though they are subjected to those things on the physical level, there's more than that. There are some behaviors and interactions that can be maybe articulated as some rule of thumb or processes that can be described, but they may not be carved in stone. I'd be very interested to see if such things can be still explored with machinery that we develop here.
One more thing, did you deal with equations that are stochastic?
So far, we haven't looked into stochastic equations. We have one work stream of a few researchers that look into stochastic partial differential equations. We believe that we have a reasonable understanding how to go about it, but we haven't yet dipped our feet deep in the water. So this is again, yes, another blind spot among many that we have in this work.
Because this could bridge your way to biology and medicine, because the life entity is not really carved in stone, as you say. There is something called fate, something called luck, and to model luck is only stochastic, of course.
I completely agree.
Yeah, thank you very much.
Thank you. A great question. Thank you very much.
Yeah, thank you. Any other questions? All right, seems not. Yeah, thank you again, Lior and Sanjeeb. So next lecture will be in exactly 2 weeks, and then the third one will be in 3 weeks. And next week there will be another seminar that I couldn't change. Yeah, yeah. Okay, thank you very much. Yeah, thanks, and yeah, see you all next week here around. Yeah, thank you.
Thank you very much.
Yeah, thank you. Thanks.